If x and y are twice differentiable functions of t, and r is a vector valued function of t given by r of t equals xt times the I vector plus yt times the j vector, then velocity is the first derivative of your vector valued function r. Acceleration is the second derivative. And remember, with derivatives, you can take the derivative of each component separately. The speed is the magnitude of velocity, and that is your x terms derivative squared plus the y component, its derivative squared, added together and square rooted. It's still the same as magnitude from what we've done in the past. Let's jump into an example. Find the velocity vector, speed, and acceleration vector for the particle that moves along the plane curve C described by r of t. Our I vector is multiplied by 2 sine of 1/2 t, and our j vector is 2 cosine of 1/2 t. Our velocity, let's take the derivative. That's going to be 2 cosine of t over 2 times the derivative of that, which is half. The 2 and the half will cancel. So here's our derivative. And then the next part, same thing. Remember, cosine, when you take the derivative, goes to negative sine. So it's actually negative 2 sine of t over 2 times a half. The 2 and the half cancel. The magnitude of the velocity, which is speed, we have this term, because it's our first derivative, squared. So that's cosine squared t over 2. And you can also, instead of putting the square here, you can put it outside the bracket. Remember from trig, those are the same thing. That 2 can also be written here. Just don't write it both places. And then our second term, negative sine t over 2, that quantity squared will get rid of the negative, so it's sine squared t over 2. Cosine squared plus sine squared of the same angle will equal 1. Square root of 1 is 1. The acceleration, we're going to take the derivative of our velocity component. So this will be negative sine t over 2 times a half from chain rule, and then minus cosine of t over 2 times a half, again from chain rule. And so this is the acceleration vector. Example, given rt equals t squared minus 4I plus tj, find the velocity and acceleration at 0 and at 2. Velocity, remember, is our first derivative, so it's 2t times the I vector plus 1 times the j vector. And then another derivative, that'll give us 2I plus 0, and that's the acceleration vector. The velocity when t equals 0, 2 times 0 is 0, so the I component drops out. We're left with j. V of 2, 2 times 2 is 4, plus j. Acceleration when t is 0, there's no t at all, so it's just 2I both times. T squared minus 4, if it's written in the x position, that's same as x equals y squared minus 4, so it gives us a sideways parabola. As you look at the vectors produced when t equals 0, which would be here, velocity moves along the path, acceleration moves inward on the concave side of the curve. The path would be given here, this sideways parabola. When t equals 2, velocity was 4I plus j, so when t is 2, we would go in the 4I plus j direction. The acceleration is still the same, it is 2I, so it's 2 units in the I direction only, which faces inward on the concave side of the curve. Another example, given this vector valued function, the velocity is 1I plus 3t squared j plus 3k. The acceleration, 0I, 6tj, and 0k. When t is 1, velocity, only plug in where you have a variable. So the 1 can actually only go here. 1 squared times 3 is 3. So the vector velocity when t equals 1 is this one. And that would be a vector velocity in space. Velocity vector in space. I said it backwards. The acceleration when t equals 1, 6 times 1 is 6. So that would be 6 in the j direction. Another example, an object starts from rest at the point 1, 2, 0 and moves with an acceleration of at equals j plus 2k. Find the location of the object after 2 seconds. Well, they give us some initial conditions. The object starts from rest. That tells us that the velocity is equal to the 0 vector and starts from the point 1, 2, 0. That gives us the initial condition. The position when time is 0 will be the x, y, and z components at rest. So that will be 1, 2, and 0. Velocity is the antiderivative of acceleration. Remember, acceleration is the position function's second derivative, but velocity is only the first derivative. So we take the antiderivative of j plus 2k, and that gives us, because j only has a 1, it gives us tj plus 2tk plus some constant of integration. Now, since there's 3 components to this, c is actually c1i plus c2j plus c3k. Since we started at rest, you plug a t in, you get all zeros. And so the velocity vector is tj plus 2tk. The constant of integration is 0, but that's again because when t was 0, this is all equal to 0. So that forces the constant of integration, all of them, to be 0, starting from rest, in other words. Now, one more antiderivative. If we take the antiderivative of velocity, we get position. T squared over 2j plus t squared k plus a constant of integration for this particular function. C is, this time, because we've done an antiderivative another time, second time, C4I, C5J, C6K. Now from rest, we were told to start at the point 1, 2, 0. So the position at time equals 0, or at rest, was 1, 2, 0. Matching this up, C4 has to be 1, C5 has to be 2, and C6 has to be 0. Going back to this part, because C is made up of these 3 different values, there is no I component after doing the antiderivative. So that means that there's only a 1 with the I component. C5 was 2, so that goes along with J. T squared over 2 plus 2, that goes with J. And then finally, the K component, T squared plus 0, just gives us T squared. And then finally, we've got our position function here. Carefully sub in t equals 2, because the location after 2 seconds is the position after 2 seconds. R of 2, that's I. 2 squared over 2 is 4 over 2, which is 2, plus 2 is 4, and then 2 squared is 4. So here's the position of the particle or object after 2 seconds. Well, yeah, it is 2 seconds. I'd forgotten where to look up here. Theorem: neglecting air resistance, the path of a projectile launched from an initial height h with initial speed v sub 0 and angle of elevation theta is described by, now it's got a very long formula, v sub 0 cosine theta times t. That gives you the position of the ball traveling downfield, or whatever the projectile is. This J component is the vertical component of the ball. Depending on whether you're given gravity in metric or English measurements, you'll use a negative 16 for G or a negative 9.8. You'll know which one to use based on the description of your problem. A baseball is hit 3 feet above ground level at 100 feet per second at an angle of 45 degrees with respect to the ground. Find the maximum height reached by the baseball. Will it clear a 10-foot high fence located 300 feet from home plate? Okay, so let's start with the first thing is our position function. V sub 0 is 100 times cosine 45 degrees. Cosine 45 degrees is square root of 2 over 2, so that gives us 50 square root of 2 t for the I component, and that's the path going away from the batter. The vertical component, the ball was hit 3 feet above ground. Initial velocity is 100 feet per second times sine 45. Sine 45 is also square root of 2 over 2. So we have 3 plus 50 square root of 2 times t. Don't forget these little t's in here. Minus, and because we're given feet, we choose negative 16. That is negative, I probably should have wrote 32 here. Let me change that. I think I mentally halved it when I shouldn't have, when I was writing the notes. Okay, so negative half times 32, there's our negative 16t squared times the j component. Then the velocity is the derivative of each component. 50 square root of 2 times t, that derivative is 50 square root of 2. Constant goes away. Same thing here, take the derivative, 50 square root of 2, and then negative 32t. Okay, so we've got our velocity function, which is the derivative of the position function. The time at max height, which is a vertical part of our problem, we're going to use the j component. Max height occurs when the derivative is equal to 0, because remember the path is going to go up and then come back down. We're looking for the top of that arc. The time it takes to reach max height when the derivative of the j component is equal to 0 is approximately 2.21 seconds. Add 32t, divide by 32, and then you can leave that as like 25 over 16 square root of 2 if you like. If you want to approximate with your calculator, that's fine too. The height at 2.21 seconds, again I'm going here, back to remember position. So the derivative is used to find the time it takes to reach max height. The position at max height, we go back to the r of t, j component. Sub in our time. 3 plus 50 squared root of 2 times our time minus 16 times time squared. That gives us about 81 feet if you use your calculator for the max height of the baseball. Excuse me. X sub t, what we're going to do with this one is we're going to find out how long it takes for the baseball to get 300 feet downfield. So we're going to take the horizontal component instead of the vertical component. We want to know when the horizontal has reached 300 feet. Well, x of t is 50 square root of t, and we're going to find out when that's 300. 300 divided by 50 square root of 2, be careful typing that in, 50 square root of 2 goes in parentheses, you get a time of a little more than 4 seconds, 4.24 seconds approximately. That's the time for the baseball to reach 300 feet away. Now the height at that time, we're going to go back to position and use the vertical component, the j component. 3 plus 50 square root of 2 times our time to reach 300 feet downfield minus 16 times our time squared. Carefully calculate this and you get about 15 feet in air at 300 feet away. So that tells us that the ball will clear the fence 300 feet away, because the time it takes to reach 300 feet away, the height of the ball is 15 feet, which will go over the 10-foot high fence. This one's going to take a lot to get it mastered. There's a lot of components. When do I use velocity? When do I use position? Just take your time, be careful, and let me know if you have any trouble.